Okay, so we're about halfway through chapter 6. The majority of it has been focused on Moody diagram. And that's where we're going to spend a lot of our time talking on in this chapter. Chapter 7, I expect I'm going to start it on Friday next week, and that will end the course. So we're coming very quickly, and there's a lot of material. Maybe I should just adjust this. So the last week, I'll probably do a final exam review and probably a course summary, but we are approaching. So anyways, chapter 7 will be about 4 lectures. Chapter 7 is 4 lectures. Chapter 6 is 5 lectures. And we are in the 3rd lecture. Okay. So design a small or smooth plastic pipe to carry 0.27 cubic meters per second of water at 20 degrees C through 305 meters of horizontal pipe. The pressure drop is to be approximately 1.72 megapascals. Find the required diameter D. And if you haven't figured it out, I'm actually doing a lot of pre-done examples, but changing the units from English to SI, and so you end up with weird lengths like that. So it's 1,000 feet originally. But if you do that, you can relate F and D just to be consistent. And if you put all the numbers that you do have, D8 U. You end up with a relationship for F, which is what you're going to be validating against, of 0.358 d to the 5th. So just substituting all the numbers you have, you know you have water, you get that from tables, and then you relate Reynolds number and diameter, and that's just going to equal 4 rho Q over pi mu d, which is 28,800 over d. So you have enough to work with there, and you would iterate back and forth. And if you haven't figured it out, I'm not a big fan of the Moody diagram, but you do have to use the Moody diagram, or you do have to know where the Moody diagram is coming from. So initial guess, F equals 0.002, which is a standard kind of thing. You get D, which is equal to 0.56 meters, substituting it in. Reynolds number equal to 5.1 times 10 to the 5th. And you update F to equal 0.0131. You then do it again, and again you're going to, these types of problems, this is type 3 problems where you're getting the diameter, you get a new value of 0.131, and diameter switches down to 0.515 meters. Your update on the Reynolds number is going to be 5.6 times 10 to the 5th, and your new friction factor is 0.00129. And after that, you get 0.0129 for F, and that correlates to diameter of 0.512 meters. So you can converge relatively quickly, and I will show you the result of my careful use of the Moody diagram. And as usual, I am able to read to 4 or 5 decimal points. And I think I did a better job with the lines on this one. There's a slight shift. You're kind of moving around between, again, logarithmic values, 50,000 to 60,000. And your first iteration is kind of a big guess. You always kind of guess something. And 0.02 often, quite honestly, seems like a good a guess as any to start with, and just sort of go from there. But the convergence happens very quickly. So in reality, if I were to use the Moody diagram to do this, my answer would be 0.013, because I can pull that out pretty easily. So 1, 2, 1, 4, 5, 3, actually 1, 2. And the expectation in the course is that you know how to use the Moody diagram. So you need to be able to use it, and frankly, it is a useful tool when it comes down to a final solution. I don't believe it's the best tool to use when you're dealing with iteration. And again, sort of same problem, delta P, same result. And I can say that, again, F is equal to 305 divided by 2. I'm not going to do that. 0.358 d squared, and Reynolds number based on diameter, same thing as before. Any questions so far? Sorry, go ahead. That's what I would suggest. So on the exam, what you will end up with is an aid sheet. So again, what I'm trying to sort of update that as we go through the course. So the aid sheet right now is 2 pages. There'll be the 3rd page with the Moody diagram. And what I would recommend is that you iterate on the Halland solution or Swami-Jain, dependent on whether or not you feel one is good or which one is better. I'm going to do an example today with Swami-Jain where it won't work. And so that's kind of a warning. But the Moody diagram should work in most cases, and so you validate against it. But you don't try. So for example, in this case, I have miraculously calculated an F of 0.0129. I didn't. I actually did it in Halland numbers, and then I plotted a bunch of lines on the Moody diagram, so it came in close. But when I do validate against, and I probably should have moved that up a little bit, so I wasn't quite, I should have been up here. So when I validate against Moody. And if the Moody diagram is way off, then I know I've done something wrong. And generally, because of calculators, that's a problem where I've entered a 0 where I shouldn't. Okay. So if you do the same thing and you guess F is equal to 0.2 or 0.02, you get D, which is the same thing, 5, 6 meters. You compute a new Reynolds number, which is 5.14 times 10 to the 5th. And I get an F of 0.013. Get a new F, or with the new F of 0.013, anyways, might as well just. Okay. That's an F of 0.130. With the new F, I get a new value. I integrate, or I solve again, and my final one ends up being the same remarkably accurate number that I got off the Moody chart. And the really tricky bit here is that I actually encourage you to do some of these lecture examples or homework, there's going to be enough of them, where you try and do this kind of iteration both ways. Howland equation on a computer is a joke. You just put it in and it will do all the iteration. You can iterate to your heart's content and you'll get it down to 10,000th, 100,000th place. But you know, there's not much to it. Any questions on this? But the better solution is always, honestly, it's this one, because your resolution on the chart is not really the resolution that we seem to present. And you can check in the text too to see how well they do. Any questions on this? You're going to spend a lot of time on it. All right, water at 20 degrees C at 11 cubic meters per hour. What is the maximum allowable roughness height, epsilon for the pipe? You have Q, and you have to convert from meters cubed to hour. And again, you're really looking back at a lot of unit calculations to make sure you're getting the right answer. So Q is given, you get a diameter of 3 centimeters, so you convert that to meters. The height difference is 2 meters from the jet nozzle, or the exit over here. So 1 to 2 to 3. And you're asked to find the maximum allowable roughness. Oh. So you can calculate your velocity. You do that by using Q divided by A, and you have 4.32 meters per second. Calculate your Reynolds number, and you have here a turbulent Reynolds number of 129,000, and you can use the energy equation. And so in this particular case, the height difference between the two is just going to be 2 meters. Okay, well, a lot of explanation. So that actually is the correct answer. I don't know why I wrote all that. Okay, so you get 3.05 meters, and you find for a roughness of 0.0192 meters for friction factor. So for a smooth pipe, or sorry, not for a smooth pipe. This is not a smooth pipe. I hope I wrote that. Okay, if you rewrite the entire If you don't want to deal with a log, which I don't want to deal with, you can raise it to power 10s. So the left-hand side of the Holland equation then becomes 10 to the power minus 1 divided by 1.8f. And we can write the rest of this as an x plus 69 Reynolds number, where x is the roughness. Oh, sorry. So x in this case is going to be 4.31 times 10 to the minus 5. Okay, square root f. Oh, and f in this particular case 0.192. You end up with epsilon equal to 0.00398. D equals 0.00. Too many zeros. 398 times 0.3, which yields 0.012 millimeters. Okay, that's crazy. So relatively small number, relatively small number, and it's not a, it's again one of those problems where you spend a lot of time sort of writing numbers into the calculator more than anything else. Questions? It's just, again, just a manipulation of the equation. Go ahead.
Isn't D given in the problem?
Oh, you know what this is? I think I miswrote. Hold on. Yeah, D is given in the problem. That makes more sense. This is epsilon over D. This is epsilon. Thank you. All right. Very small roughness factor. Okay, I got lazy. Actually, I didn't. So I think a valid question is, what do I do if I have to deal with English units and have to solve a problem? Convert, convert, convert. You can deal with slugs. You can deal with pound masses, pound forces. I often get very confused with those, and I find it's easier to convert and convert back. So again, a decision you have to make as you're solving problems. 75% efficient pump moves water at 3 cubic feet per second through 2,000 feet of 6-inch cast iron pipe. What horsepower is needed? You're given Q, you're given D, you're given length, you're given delta Z, and delta Z is 120 feet. You're getting cast iron, which is 0.00085 feet in terms of height, and eta of the pump is given. Okay. Again, when I present these problems, I will solve them in SI and then present you solutions. So I did change back here so I stay consistent. We are supposed to present stuff in English units. Please get used to them. You will do lots of stuff with them at some point. So So this particular problem, the answer is 0.00027. And I can use the Holland equation to do that calculation. And the Holland equation ends up with that. I mean, the book says it gets 0.01 or 0.227. I can't, but I can get it with this. And so the alternate approach that I had mentioned yesterday also applies, and you can still do things with the Holland equation or the Swami-Jain equation, and I'd certainly encourage you to do these examples with both. Questions? Sorry. Okay, nothing to it. So in terms of energy, you have the energy out, HP, which is equal to 120 plus 0.0227 to, okay, no, 2,000 over 0.5, 15.3 squared over 232.2, which equals 450 feet. Power is equal to rho G Q HP over eta, and that will equal 112,200 foot-pound force per second, or approximately 204 horsepower. Again, if you look at the 8 sheet, there is an equation for power in there. So one of the things that we're not expecting you to memorize that, but you should be aware of where it is so that when you ask me a question during the exam, I can say, please remember it's somewhere available to you. Okay. All right. So that's that problem. Okay, this is the one that messes everything up. Now, but this is kind of interesting to sort of start with. I have two pipes. I have pipe 1, which has a length of 10 meters and a diameter of 6 centimeters. Pipe 2, which has a length of 30 meters and a diameter of 4 meters. And they're attached to a tank which is 20 meters, has 20 meters of water at the top. In between there is a turbine. And so the turbine is going to take power out of the system. And so you are associating that with a pressure drop. And you have a delta Z 20 meters pressure out, or a power out, excuse me, of 400 watts. So 20 equals F1 L1 D1 V1 squared 2G plus F2 L2 D2 V2 squared over 2G plus P over rho GQ plus V2 squared 2G. Okay, so this is an equation where now I have two velocities, the one in the first pipe and the one in the second, because of course, even if mass is the same, the velocities in the larger pipe are going to be less than the velocities in the smaller pipe. And I also have an exit at the end, which is where I'm going to be fitting everything to, which is the jet or the tank exit at the very end of that. I'm going to guess a flow rate. Then I'm going to iterate or calculate V1, RE1, V2, RE2. Then with epsilon over D1 and Reynolds 1, find F1 using Holland. With epsilon over D2, find F2 using Holland. And again, as much as possible, I am not going to use the Moody diagram to do this. I will depend on sort of getting the right answer. Substitute all values into the energy equation, see if it balances. Adjust Q until the equation holds. So you can see there's a lot to this. And it's going to be higher order in Q. So you're going to have at least two solutions. Yeah, you have two solutions. So if I do that, I end up with something that you can spend the weekend with. Oh. And it really is an Excel problem. You put in the Holland equation, you iterate a couple times. You can iterate to your heart's content. But once you do that, you'll find two solutions. One, which is Q is equal to 15.7 cubic meters per hour, or Q is equal to 9 meters cubed per hour. And then the question is, which one is the preferred solution? Let's see. So efficiency, you probably want to go with B, 43% less. Water flow for the same 400 watts power, which is great. And it's the more efficient operating point. In solution A, the head losses are so large, the turbine head required or remaining is very low or small. And real turbines have power curves that increase with flow rate. It's unrealistic that this turbine would produce the same power at a much higher flow rate. So, I mean, a secondary consideration when you design these sorts of systems would be you'd have a power curve for that particular turbine. And you'd start to consider that as you design the system. Everything is dependent on energy equation. We've done lots of examples on this. We've looked at different types of approaches. You have the 4 types of solutions that you have to look at. And for Reynolds number in this course, or sorry, for pipe flow in this course, laminar flow is a condition that occurs below 2300. Turbulent flow occurs above 4000. And you can find the head loss directly from Poisson's law for laminar cases. For turbulent ones, you get the friction factor off the Darcy-Weisbach equations. In both cases, you're just sort of fitting everything through, and you're looking at different ways to solve things. We also have a magical jump in this course. Nothing happens between 2300 and 4000. So somehow something magical happens in all of the numbers that you ever deal with. But in reality, there's a transition between 2300 and 4000. So as far as the solutions are concerned, just 2 seconds. That's what you concern yourself with. Go ahead.
Before you talked about how like it gets weird around like 21,000 to 28,000, so would that be like from 21,000 to 40,000?
I'm sorry, 2300 to 4000. Yeah, in that range, in between the two. I may have misspoke. From 2300 to 4000, it's transition. And you have a mixture of laminar and turbulent flows that occur. And because of that, all of the stuff that you kind of learned is not as useful here. There is some, but it's not as helpful. And you'll notice that when you look at the Moody diagram, where it stops for turbulent flow at 3500, and you have a range for laminar flow, which is up to about 2300. So there's this gap in your data. The Howland equation, super. Powerful explicit tool for finding the friction factor in turbulent flows. And in fact, I would strongly recommend getting comfortable with it because it's a faster way to solution and a less cumbersome way. It's kind of painful on a calculator, but once you kind of make sure you write very carefully, it's a lot of bookkeeping. That's about it. But you do have the Moody diagram as a secondary validation step or verification. With type 2, type 3 problems, you have a lot of sort of iteration where you go back and forth until you have a solution. And sometimes you end up in weird cases where you have to consider what's happening, say, with a Q squared or something of that nature. And finally, we get a lot of solutions to the equations, and really your job as engineers is to consider the efficiency and the realism and find the best operating point. We start to look also, and I'll talk in more detail, I think, about this, at non-circular ducts. And we use something called the hydraulic diameter, which is basically 4 times the area divided by the perimeter. So essentially switching whatever geometry you're looking at into an equivalent circle. So you can do that with squares, you can do that with whatever you're looking at, but P is the weighted perimeter, the outer portion where friction occurs. And you can define Reynolds number in those cases using hydraulic diameter and the roughness with hydraulic diameter. And again, and use these values, and use these values in the Moody chart. And the guidance is that it's worth plus or minus 15%, which is true. But again, your accuracy, my accuracy on the Moody diagram is probably at best 20%. If you have two parallel plates that are separated by a distance 2h, thank you. Okay, 2h. The hydraulic diameter is 4h, so 4 times the base times the height, 2h, and divided by the wetted area, which is 2b. So you end up with 4h. For laminar flow, you can use a friction factor that's going to change a bit, 96 over Reynolds number. For turbulent flow, again, you can use the hydraulic diameter with an effective diameter that is 0.64. If we were to ask you something like this on an exam, we would tell you some of this so that you would have guidance. But we are not, but it's important that you kind of have some idea that this is there. A common sort of issue is annuluses. So you have a pipe within a pipe, and the area of the outer pipe is going to be, if the inner pipe is A radius, outer pipe has a radius of B, you're going to find that the area is A squared minus B squared times pi, just the difference in the circle areas. Perimeter 2 pi A, 2 pi B. Hydraulic diameter is going to be, after you do the numbers, 2a minus b. And for turbulent flows, you use that number, which is probably reasonable. So these are a lot of empirical relationships that you end up using to solve these issues. unlike circular pipes, you always have secondary flows. So if I take a look at the flow coming at me, that's what it looks like in this component, or this side right here. However, within the plane, there's also secondary motions. And those secondary motions are circling among themselves. So in each of the corners, you'll have two vortices that appear. And here you'll have a single vortex, because that's just where it's going. That's to the midplane. And you have rotation of the fluid in there, which changes the characteristics. If it were a circular profile, you wouldn't have these secondary flows. And so that's one of the reasons why generally, in most cases when we deal with things, we prefer circular pipes, because secondary flows are not a problem. In heating and ventilation, we do have some limitations. So for example, it's a lot easier for a technician to put together a rectangular duct than a circular duct. And you can ship that as flat plates, and that's why they end up doing it. So I want to do a couple final questions on this and just sort of look at what's happening. Water drains from a reservoir, 0.5 meters high, length of 100 meters, delta Z 20 meters steel, which is epsilon of 0.046 millimeters, and you find Q, write the full equation. And maybe I'll write that here. So delta Z equals head loss plus V squared over 2G, and V equals 2G delta Z over 1 plus FL over D, and L over D equals 200. All right, I mean, that's basically the whole step. And here I use Swami-Jain. But I end up in a bit of a jam. And the reason I end up in a bit of a jam is that, well, I'm going to do iterations. So guess F equals 0.02. V equals 8.86. I get a Reynolds number of 4.43 times 10 to the 6th, and a friction factor of 0.012. V equals 10.74 meters per second. F equals 0.012. And I have Q, which is equal to 10.74 times pi 0.5 squared. Whoops. Oh, no. Sorry, divided by 4. And I get 2.1 meters cubed per second. And if you remember from yesterday when I presented that, I had a relationship for Q out of Swami-Jain. And if I use the Swami-Jain relationship, I end up with Q, which is equal to 3.96 meters cubed per second, which is wrong. And the reason for that is that Swami-Jain ignores kinetic energy. And so this is one of the reasons why, as you're going through these problems, you really want to make sure that you check against something else. So iteration on F is usually enough. And if you want to be cautious, you can always check. You can also go back and use Swami-Jain in those kind of cases and say, hey, I've got a result. What does this make sense? And if it does, then you're set. And I don't need that one. So I'm trying to give you all the warnings about Swami-Jain. I still think it's a remarkable equation. Well, let's do something in English units. Everybody loves English units. So we have Q equals 3 cubic feet per second. HF is 4 feet per 1,000 feet. So the head loss, okay. Epsilon 0.005 inches, and nu is equal to 1.22 times 10 to the minus 5 feet squared per second. Find diameter. And this is, again, one of the cases where you could use Swami-Jain. So you go 8 times 0.15, and I kind of regret I didn't rewrite the equations here, but I have them at the end. 1,000 times 9 pi squared 32.2 4 0.968 feet. And F from Swami-Jain ends up being 0.017815. So I went a little bit crazy with my numbers. And when I do that, I can't read anything to that kind of precision. But you know, 0.018 is probably a reasonable number that I could get off the Moody diagram. If I use Swami-Jain, or sorry, that's the new iteration, so it's the new F. So 0.017815, diameter equals 1.002 feet. V2 equals 3.81 feet per second. F of Swami-Jain is 0.01770. So not a huge change here at the 10,000th place, and you shifted from 0.017815 to 0.017770. That's a pretty heady convergence. And you can continue with that. And if you do that, you end up with D, which is equal to 12.02 inches, and F of Swami-Jain, which is equal to 0.01771, which is a converged value. So you have a diameter which is 12 inches. And HF for that is calculated out to 4 feet, and diameter equals 12 inches. So that checks out. That's good. We can also use the equation that we had, equation 2 from the last lecture, 0.66, 4.17 times 10 to the minus 4 to the power 1.25, 69.88, 4.75 plus nu q to the 9th plus dot 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 5.2 to the power 0.4, and yay. $13 inches. And the error is coming about because of this q to the 9th term. So if I have to do q to the 9th and I take it all the way through and run all my calculations through for all of these terms, I get to the precision of my calculator, and my error starts to go by 10%. And there you go. So it's great. I really like these equations, but there are limits. And if you noticed, just 2 seconds. If you notice when I introduced them yesterday, I put a small little note on top saying best with SI units, it's best with SI units. Go ahead. It's a whole bunch of numbers, and I didn't want to write them out. But if you look at the final slide of the lecture from last time, and I probably have put it in here somewhere, you'll see it. Yeah, there you go. So you have all of that, and just one other thing. Excellent. So you get that 13.1 inches. You know, the result with Swami Jain, 13.1 inches, diameter 12 inches. Generally, you're safer to do iteration. And if you do iteration, you calculate your friction factor, then you come back. And one of the problems that is very clear from this is that if you do the conversion, and I didn't, but I encourage you to do that, you could try it again with SI. And again, this is great work for you to enjoy over the weekend and think very hard about fluid mechanics. So, a whole bunch of solutions. You can do it a whole bunch of different ways. You are required to know how to do it on the Moody diagram. You have the option of doing it any way you want to. So find HF, find Q, find Q, find D. And those are the final answers for all of those problems. So those sort of work out really well. Iteration is usually safe, and it's pretty painless, to be honest. Explicit equations like Swami Jain, great for quick estimates, and a great starting guess for your iterative calculations. Always for complex systems, use iteration. As soon as things get a little bit more complex, and on Tuesday, we'll talk more about this, but on Tuesday we will look at minor losses, which are major losses in a piping system. We're going to have to consider that. So you have to iterate. So problem 3 becomes more problematic. US customary units. Iteration is more reliable and avoids the numerical sensitivity of the explicit formulas, like the last one. Yay. Okay, learn slugs, learn pound force, learn pound masses, GC, G. You should know all that stuff. All right. Bottom line, when in doubt, the iterative approach is the most robust and accurate method in all cases. So you are safe using the Holland equation. You are safe using the Swami Jain. And in any example that I did in the course where I did F and used the Holland equation, go back and try it with Swami Jain and convince yourself of that. Both approaches should get you the same result. And ultimately, you want to do something. You want to do something where you have validation or verification with the Moody diagram. I strongly recommend against doing what I pretended to do on all of the examples where I drew all the lines on the Moody diagram. All right, thank you. I'll see you on Tuesday. Okay. I'm going to get lunch. I'm going to get lunch. I'm going to get lunch.